Well, it's great to be back from Seattle to Santa Barbara. The weather change I'm still getting used to in Seattle. It's nice to have more sunshine right now. And so I'd like to start off by just acknowledging some of my funding sources: University of Washington, NASA, and National Science Foundation. And of course, it's great to be here at the Kavli Institute. I've been here for the last 3.5 weeks and departing sadly on Friday. And it's been a great visit. So today I'm going to tell you a little bit about this fairly brand new field, brand new in that it wasn't around when I became a graduate student here at UCSB. It's the field of extrasolar planets, which has now been shortened to Exoplanet, which is a little easier to say than extrasolar planet. And by exoplanet or extrasolar, it just means outside the solar system. So these are planets that we're finding orbiting other stars. And it's a very exciting field in that a lot of astronomy, like black holes, doesn't relate to our everyday life. But when you talk about planets orbiting other stars, given that we are planted on a planet, it's easy to imagine what they might be like. And imagining what they might be like is what this picture is all about. So this is actually a planet I discovered. I'm not planning to talk about it today. In a planetary system about 1,200 light years away. And it's being compared in this graphic to our solar system. This picture, though, is completely fiction. It's just an artist's impression of what this planet might look like because we only discover its effect on its star indirectly to infer the presence of that planet. Now, this topic has been around for a long time. Giordano Bruno made this great quote about the possibility of there being, since there are countless suns, maybe there are countless Earths out there rotating about their suns in exactly the same way. And so that's a really interesting prescient point as the 7 planets of our system. We see only the suns because they're the largest bodies and they're luminous. That's also important. That's why this field is hard and why it's only recently that we found planets around other stars. What's that?
They burned him alive.
Exactly, yeah. partially for this quote, actually, I think. What was that? Sorry.
Interesting that he spoke English.
This is a translation, thank you. But their planets remain invisible to us because they're smaller and non-luminous. It's not quite correct, actually. They are luminous, but very, very faintly. And the countless worlds in the universe are no worse or no less inhabited than our Earth. Now he's really going out on the limb. But that's really why this field is exciting, is for that last sentence, that we could imagine life being on these other planets. And so the reason I think this has drawn a lot of attention from NASA and from other space agencies around the world and scientific agencies is that when we do science, we like to have large statistical samples that we can study. When you're studying a planetary system, if you only have one example of a planetary system, then you can always tune your model to match that system. And so models of the solar system have been biased by the fact that we live in our solar system, and they've been possibly designed to match our solar system. But whether they can match other solar systems was an open question until we started finding planets orbiting other stars. This then gives us clues for how planets might form, and by finding examples of many planetary systems orbiting other stars, we can test our models of planet formation, and then that feeds back, and it has fed back into our understanding of our own solar system. So it's been a very fruitful field for understanding the planets that are near and dear to us around our sun. Then the other big philosophical questions are how common are planets like our Earth, and if so, is our Earth very special, or are Earths everywhere around other stars? In addition, if we were going to find life elsewhere in the universe, we've searched our solar system. There may be still a possibility of some possibly microbial life in our solar system. But planets seem like a good place to start, given that we live on a planet. So finding planets always has that exciting undertone of possibly finding life. Now, what makes this field hard, as alluded to in Bruno's quote, is that planets are very, very small and faint compared to a star. This shows a diagram. This is a log scale, so each of these numbers, 0, 1, 2, on up to 12, represents a factor of 10 in brightness. And so you can see here that the sun, in the optical wavelengths, this is wavelength on this axis. So in the optical wavelengths that we can see with our eyes, so that's in this part of this diagram, the Earth spectrum, which is this black line down here, is about 1 billion times smaller or fainter than the sun. So when you're looking at other stars, to detect a planet like our Earth requires seeing something that's apart in 1 billion relative to that star for a star like our sun. Now, one way to look for Earth is maybe to look at fainter stars, but that only buys you maybe factor of 1,000 or 10,000. Still a hard problem to find planets like our Earth. One way to improve the chance of finding something like our Earth is to move into infrared wavelengths. Santa Barbara is a hotbed for infrared detectors, actually. In the mid-infrared, at around 10 microns, the contrast improves to just a part in a million, but that's still a very large factor. And so when we look at other stars, it's very difficult to see if they have planetary systems around them. However, we have, in fact, done this now. We've both directly imaged and detected indirectly the evidence of planets orbiting many, many stars. And there's two primary channels that we do this. The first technique that took off in the 80s, late 80s, early 90s, was due to the gravitational interaction of the planet with a star. So Einstein's relativity isn't really necessary, but this is the equations describing that. Newton's laws are actually good enough, the approximation of relativity, that you can describe a planet's orbit around its star as gravitational interaction that not only causes the planet to orbit the star, but also causes the star to orbit the center of mass with that planet, and indeed with all the planets in its planetary system. That motion of the star about that center of mass with all the planets then creates a Doppler effect of light being compressed as the star comes towards us, and light being stretched as the star moves away from us. And that then is known as the radial velocity detection technique. And this is one of the primary ways that planets have been found around other stars. There are other techniques that rely on the gravity of the planet. I will be talking about one of these today, which is timing, and I'll explain that in more detail. But all these have started to pick up speed in the rate at which we've been able to detect planets around other stars via the gravitational interaction of the planet with its star or with the other planets in its system. And the other way we find planets is through the electromagnetic interaction, either light reflecting off the planet or being absorbed and re-emitted in the infrared, which is what gives you that favorable contrast in the mid-infrared, or by detecting the shadow of the planet. And that's the technique that's known as transit, which I'm going to be focusing on today. In some cases, for very hot planets orbiting very close to their stars, we can see the planet disappear as it goes behind the star, which is referred to as a secondary eclipse. And this is best seen in the infrared for hot planets that are radiating at a high enough temperature that you can see their emission in the infrared and see the planet disappear as it passes behind the star. In addition, we're starting to develop the technology to do direct imaging of planets around other stars. And if I have time at the end, I could talk about some of the future vision that NASA has for doing this. This requires suppressing the light from the star by this factor of 1 billion in the optical, which is really hard, or 1 million in the infrared. And in doing so, then you can see the planets directly in either their reflected light or their infrared emission thermal heat as they orbit the star.
So Eric,
yes.
Can you tell us the speed for the radial velocity for the sun? How much is it moving around the planets around it?
Okay, so the sun is moving a few meters per second, maybe 10 meters per second due to Jupiter, which is a very, very small speed. So you can, so it's running or speeds or so. And making those measurements is extremely challenging. A lot of those measurements have been made with a telescope that the University of California has built in Hawaii called the Keck telescope. And one of the reasons that telescope is great is because it's a very large telescope, so you can collect a lot of light from stars and you can make more precise measurements than it's possible with other telescopes. So the radial velocity technique has found, up until recently, it had found the most planets around other stars. But the transit technique has actually overtaken that. And I'll explain some of the reasons why that's the case. You can see that actually in this diagram. So this shows as a function of time. This is starting in 1989 with the first detected planet. This actually wasn't recognized as a planet at the time. This little blue curve here, histogram here, this goes from 0 to 200 on this axis, and then this is just linear time from 1988 to 2013. 2014 actually would be off this chart because they found a lot of planets last year. The colors represent the detection technique. Blue is the Doppler shift technique. And that, you can see, was how most of the discoveries were made very early on. When I was a grad student at UCSB in 1992, which is this time right here, the planet system was found around a neutron star, a pulsar, from the radio emission of pulses from that neutron star behaved in a slightly irregular manner. They sometimes came early, sometimes late, and then it was realized that this pulsar hosted planets around it. The formation of those planets is still a mystery, given that pulsars, we think, formed from a supernova explosion. Stan Peele actually worked on the mathematics to confirm that these were, in fact, planets. Stan is an emeritus professor in this physics, UCSB physics. So when I was a grad student, I worked with Stan my very first summer. And I thought, well, with only one planet system, this one wasn't really recognized at the time. There were 2 planets in that system. I didn't want to stake my career in that. So I worked on black holes for quite a while and then picked up on exoplanets in the 2000s when you can see these numbers are starting to build. What really made exoplanets convincing, though, was this tiny little green bar here in 1999, which is green is the transit technique. And so that's when the first transiting planet was found around another star. And I'll explain what that means in just a minute. And then you can see that this field is just growing by leaps and bounds, and lots of these different techniques are finding planets. But now we're really dominated by the transit technique, and there's a reason for that. Now, what is a transit? Well, it's fairly simple to explain. It's a planet blocking the light from a star. This shows a transit of Venus. This is in the ultraviolet, I believe, and so the sun looks fairly non-uniform, but usually the measurements are made in the optical where the sun is more uniform. It's dimmer towards the edges than it is towards the center. And so if a planet in its orbit happens to pass in front of a star, it'll block a little bit of light from that star, and you'll see that star dim for a few hours, and then brighten back to its normal brightness. Stars are always varying, though, which causes a problem. But the nice thing is that if a planet is orbiting in a regular orbit, you'll see this repeated dimming will happen every orbital period. And so that builds confidence every time you see the planet dim the star, that it's actually a planet and not something else that's causing that dimming. The problem with this technique is that it requires a special geometry. It requires that the planetary system, or at least the planet that's transiting, has to have an orbit that just by chance lies edge-on to our line of sight. And so you'll see the planet pass in front of the star. That's improbable, but the way to win the lottery is by buying a lot of lottery tickets. And so if you observe enough stars, then you can hope that one of the planets will eventually transit. Now, we can't see the detail of another star like this. We only see a point of light because stars are so far away that all the light from those stars is just summed into one single pixel on our detector. And so the way to then detect this is just by measuring the shape of the brightness of the star as it declines. So this is a nice diagram due to Josh Wynn, a professor at MIT, that shows for a very close-in planet what the orbit looks like on the top and then what we measure on the bottom. And he's drawn this so that time actually goes in a circle here And the relative height of these lines represents how bright the star plus the planet is. This diagram is actually made for infrared observations where the planet is so hot that it's emitting a significant amount of radiation relative to the star. And the 0 point on here is way down below this floor here. So this is just zooming in on the very top part of what we call a light curve, which is just how bright the star is as a function of time. And the main point is that when the planet goes in front of the star, we can see the star dim, in some cases by a few percent, which is easily measured from the ground with a modest-sized telescope. So this has been an exciting field for amateur astronomers because they can actually make measurements of these transits. They can detect planets, the shadows of planets, with a modest-sized telescope. It's really exciting. In this diagram, the star or the planet, as it goes around, we start to see its side that's facing the star that's hotter. And in the infrared, that would cause the planet to brighten. And that's something I've worked on in the past. And then as the planet goes behind the star, then you see what's called the secondary eclipse as it disappears. Now, this sort of measurement would be very, very difficult for the Earth around the sun because, as I mentioned, the Earth is 1 billion times fainter than the sun, or 1 million times fainter in the infrared than the sun. And that dip is very hard to measure. But for close-in planets, it turns out to be possible to measure.
You mean close to the stars?
Close to the stars that they orbit, yeah. This transit technique, you saw that rise with time in the diagram a couple slides ago. It was taken over by the green, which is the transit technique. It was made possible by an incredible NASA mission called Kepler. This shows the telescope here. It's a fairly boring experiment in that for 4 years, this telescope was pointed at the same location on the sky continuously for 4 years. Every 3 months, it would rotate by 90 degrees. This is a shutter at the top, and the light comes in, bounces off a large mirror, and then is focused to a very wide field charge coupled device detector. And this shows where the detector lies on the sky. There are actually something like 40 detectors. There are 2 pairs of rectangular CCDs. And this covers a fairly large part of the sky as far as astronomers are concerned. Just to show you what I mean by that, this little blue dot here, I'll zoom in a little bit so you can see that. That little blue dot is the field of view that the Hubble Space Telescope can view. And actually, it's even smaller than that because the Hubble only has a portion of that blue dot that's covered with detectors. While the Kepler spacecraft was designed to observe as much of the sky as possible, and this is about 10 degrees across, so roughly if you hold out your arm with your fingers spread, then it's roughly that by that is the amount of sky that Kepler covers. And within this detector are lots of stars. They actually had to design it so that really bright stars fell in gaps because they could cause problems with the rest of the detector. A lot of stars fell within the field of view, but only certain stars' data could be sent back to Earth because there was so much data being taken by this telescope that there was no way to send it all back to Earth. It's a huge amount of data it was measuring. And these data, in some ways, are completely boring. I'll show you one example. Let's see if this shows up. Yeah, so that's the data from the Kepler spacecraft. What this shows is how bright a particular star is from 0 to 1. So 1 is just, I've taken out the average brightness of the star. So 1 is just the average brightness. And then this is versus time over about 4 years. And you can see what stars look like over time. They just look like a straight line. They're pretty boring. And stars are very stable objects. They undergo nuclear fusion in the center. They're a controlled nuclear fusion device, fortunately controlled so they're not exploding. And so they are fairly boring, which is actually good because then if a transit of a planet occurs, then you can see, wow, that star got dimmer and there's a planet there. If I zoom in on this by a factor of almost 1,000, now you can start to see something interesting. The first thing you see is that there are these fluctuations in brightness, and that's mostly due to quantum mechanics. It's due to the fact that photons from stars are individual particles, and when you're measuring light coming from a star, you're counting individual particles. And when you make a measurement, in this case, the data were sent back to Earth every 30 minutes. And so every 30 minutes, they'd measure how many photons landed on that Kepler detector from that particular star, one little part of that detector. But the rate of photons hitting varies a little bit with time. Some 30-minute segments, you get a few more photons, sometimes a few less. The more photons you measure, actually, the scatter in this curve decreases. So the brighter the star is, the more photons you get from that star, the fluctuations become smaller when you average by the mean number of photons that you detect. But, okay, so there's a scatter here, but you can also see there's these intriguing little dips here. These little rain coming down from this noise. That's not due to quantum mechanics. That's due to a planet. And the planet is blocking this star every 16.7 days, which is remarkable because this planet orbits much, much closer to its star than any of the planets in our solar system. So Kepler has greatly increased the number of planets that we know orbiting other stars. Just within that Kepler field of view, by the way, that field of view that I showed you in the last couple slides ago, it's 10 degrees by 10 degrees, or about 100 degrees squared. That's only 1/400th of the entire sky. So if we could build 400 Keplers and look over the entire sky, we would have found a huge number of planets relative to what Kepler's found, which is still pretty amazing. It's in the thousands now. This is a diagram showing the planets that were known before Kepler flew. These were discovered with ground-based telescopes. These are very big planets on very short period orbits that enabled the detection with a ground-based telescope. So 3 planets within this whole field of view. And then after Kepler flew, one of the initial data releases, this is actually out of date now, because if I showed the current diagram, there would be dots almost everywhere. But this shows the yield of planets discovered with Kepler, where light blue is an Earth-sized planet. Yellow is now a planet that's a little bit bigger than Earth. Orange is a planet the size of Neptune, and red is a giant planet, like the size of Jupiter. And you can see that those dots cover a wide range of the stars here. And we know because of this transit technique that the geometric probability of a planet going in front of a star is small. So there has to be many more planets whose orbits are inclined, and so we just don't see them. So there's basically planets everywhere. And if you do the statistics, basically every star has planets or planetary systems. This shows a diagram now of the mass of a planet. These are log units in units of the mass of Jupiter, which is 300 times the mass of the Earth. So Jupiter actually is this orange dot right here. And then this is the distance of the planet from its star. And then again, this is a log scale. 1 is an astronomical unit, which is the distance of the Earth from the sun. So we use that as a place of reference. And then the mass of the Earth is about 1/300th of the mass of Jupiter. So the Earth is down here. Venus just inside the Earth. Uranus, Neptune, and Saturn. Mars and Mercury are actually off the chart, below the bottom of this chart. This shows the status of the detection of planets around other stars as of yesterday with the radial velocity technique, the Doppler shift technique, which is shown in blue here, which I'm not planning to discuss much today. And then microlensing technique is the green dots here, and direct imaging are these kind of orangish dots out here. The planet has to be far from the star so that you can see it directly, and that's why these orange dots lie all far away from their stars. Now if you add, okay, so one thing to notice here is that there are a dearth of planets down here. And there's a basic, obvious reason for that. The further a planet is from its star, the less speed or less Doppler shift is caused by that planet on that star, and so the harder the planets are to detect. The less massive a planet is, then also the less it influences its star. And so down here, the planets are hard to detect. So this is just a selection, what we call a selection effect down here. These other techniques, though, are sensitive to different types of planets, so they kind of fill in parameter space. So the really interesting thing about this is that our solar system has a very unique pattern that was described really well by planet formation theory. So out in the outer reaches of our solar system, far away from our sun, the gaseous disk out of which we think our solar system formed, because all the planets are orbiting in the same plane in the same direction, was very cold. Cold enough that ices could condense, and so you could form very large planets out of those ices. While closer in, those ices evaporated, and so you could only form planets out of heavier elements. And so silicon, iron, oxygen. And so the rocky bodies close to our sun with small mass, because heavy elements are not very abundant in the universe, versus the giant planets out in the colder regions, that was a pattern that was predicted by models of solar system formation. The reason it was really, I'm saying predicted, is we already knew the planets were there, so you can't do a prediction if you already know the answer. But models for our solar system were designed to predict that small planets should be close to their star and large planets far away. What we found with the first detections of planets around other stars is this does not hold for other stars. There are all these giant planets up here that are orbiting much closer to their star than the giant planets in our solar system. So that was a big surprise.
But is that because that's the way it is, or because your detection methods favor a collection of blue ones?
So the question is that because that's the way it is, or because our detection methods favor these? If every solar system was like our solar system, then we would not have detected any of these, even though we'd be capable of doing that. That's one of the reasons I didn't go into this field, because I didn't know that we'd find all these planets up here. It was a big surprise. So it's because it is the way it is. The reason we don't find them down here is possibly because of selection biases, that we just can't detect these quite yet. So this really is the way it is. Now, not every planet, or not every star has these large planets close to the star, but those are the ones we can detect. So then you have to look at the statistics of how frequent these planets are, and it's not an overwhelming fraction of stars that have giant planets close to them. So the solar system may still not be that much of an outlier, but we don't really have enough data out here to really tell how common our solar system is, so it's still an open question.
Does the Doppler effect, wouldn't it be much more complicated if there are like 7 or 8 planets like ours?
Yes.
Because the wobble would be very complex because they're not all arranged in order.
Yes, and this leads to big fights in the literature over how many planets orbit a star. In fact, some of those fights are going on right now. And just in this last week, I saw 2 papers arguing over whether a star has 5 planets or 7 planets. And so the good thing is that the modeling is not too complex. It's just whether you have good enough data to convince yourself that there are more than one planet. The record holders now have something like 6 or 7 planets, but usually that 7th planet is questionable. So that's a really good question. That is.
But the complexity of finding 7 unknowns.
So if you have 7 planets, you need a lot of data to convince me that you really have 7 planets, and that's because you can look at the frequency as the star comes towards you and away from you. If you get enough data, you can actually see all the frequencies of all those different planets orbiting at their own orbital period, which is pretty amazing.
Really, you mean computers can do it?
Computers can't. Yeah, I can do it. But once you plot it over, you can see it by. But that's a really big question right now. As we push to smaller planets, the data are becoming less good, and that's exactly why we can't detect these quite yet.
How long have you been receiving the data from Kepler?
So Kepler now turned this diagram into this. So all these red dots are discovered with Kepler. Kepler made measurements over 4 years, from 2009 to 2013. And then it had a malfunction, which now it's still taking data, but it can't take the same data on the same part of the sky as it is now, or as it did during this initial mission. These red data points now show that there's a lot of planets orbiting very close to their stars, and a lot of these planets are larger than Venus and Earth. This was a big surprise. So you'll notice in our solar system, we have the giant planets out here, and then there's kind of a gap in mass between Earth and Venus and Uranus and Neptune. But when we look at other stars, there's a huge number of planets that are in between the terrestrial rocky planets and the ice giants out here. And yet they orbit closer to their stars than Venus or Earth is to our star. This is really bizarre. And so understanding this is actually one of the goals of this workshop. And in particular, one thing we'd like to know is what are these little planets made of, as Lars mentioned. And that's challenging because what Kepler does, okay, so the blue points are measured with the Doppler shift technique, and the red points are measured with the transit technique. And not all these planets are detected with both techniques. And so some of them, the red points, we actually know the size of the planet extremely well because we know how big its shadow is. And with stars, we can measure their sizes fairly well. So we can measure the size of those planets as far as their diameter extremely well. The blue points give us the mass of the planet because how massive it is, it tells you how much it causes its star to orbit around its center of mass with the planet. But we need both the Doppler and the transit technique, or another technique, which I'm about to get at the masses of these and the radii of these planets. If we have a mass and a radius, then we can get the density of the planet, and the density tells us something about what that planet's made of, if it's made of iron or rock or something else. So this is the state as of yesterday, something like 1,500 confirmed planets orbiting other stars. And there's another 2,000 to 3,000 planet candidates that are waiting in the wings for further study to confirm that they are actually planets that have been found with the Kepler spacecraft.
Are there differences in the character of the stars as well?
Yes, there's a lot of differences in the characters of the stars. So this is just showing how far these planets are from their star. But if the stars have different masses or different luminosities, that will definitely affect the planets. And that's actually a really good question because the type of planet you find as a function of distance from the star appears to be a very strong function of what type of star it is.
I think those stars would be a lot different from our star.
For sure, yeah. And the blue points were primarily targeted, well, a lot of these stars were chosen to be kind of similar to our sun, not completely though. And there's other patterns that you see here. For instance, there are no planets out in this region here. And this seems to be a true deficit because these would be easy to detect. They're close enough to the star and they're big enough that we should have detected those. And there may be other features in this diagram that we're still struggling to understand, actually, and that's a big part of this program. But looking at the planet frequency and type of planet as a function of the type of star is actually a really interesting question. There's definite patterns that we see that we're still trying to understand. And so usually when you can divide this data up by the type of star, but then you have fewer data points to work with, and so your statistics become more uncertain. So trying to compare the types of planetary systems across different types of stars will require a lot of data so that you can finally divide what type of star it's orbiting to determine kind of what type of planetary systems those particular stars have. Now, the Kepler spacecraft produces curves that look something like this. So you can see, again, there's this quantum noise. Some of this might be due to the star varying. I've, again, zoomed in the axis, and now I've folded all the transits to all align with one another. And you can see that even though there's this scatter in the data, when you line it all on the orbital period of a planet, which you don't know beforehand, but you can try a bunch of periods until you get this alignment, then you can see that there's a dip in brightness as the planet shadow crosses in front of the star. And notice that the depth of this, if you go across, is about a part in 10,000. 0.999 right here is about the depth of the planet. That's part in 10,000. That's about the ratio of the size of the Earth to the Sun. And so with Kepler, we in principle can detect Earth-sized planets. This star turns out a little bit bigger than our Sun. So this planet's a little bigger than our Earth. The other thing you'll notice is that there's this curvature here, and that's due to the fact that stars are brighter in the center than they are on the edge. And so as the planet crosses the star, it makes a slightly deeper dip when it crosses the center of the star. And that's something I have code that computes that. Now, okay, so, I actually meant to erase this. Oops, sorry. I was practicing beforehand. Okay, so now that Kepler has found all these planets that you saw there, and a lot of them actually are this new class of planet that we call a super-Earth or mini Neptune, because they're kind of in between. They're bigger than Earth and they're smaller than Neptune. We want to know what these planets are made of. Are they more like Earth, which is the super-Earth term? Are they more rocky in their composition? Or do they have a lot of gases and ices like Neptune and Uranus? Well, to do that, Kepler gives us the radii of these planets fairly precisely, and so we'd like to also measure their masses. But it turns out that one disadvantage of Kepler is it's looking at this 1/400th of the sky, and so a lot of the stars it's detecting planets around are really far away. The farther the star is, the less precise the Doppler technique is for measuring the masses of planets, and so that can make it challenging to measure their masses. Now there is another approach, which is to use other planets to measure the mass of a planet. So a lot of the planetary systems that Kepler has found have more than one planet orbiting the same star. A lot of them are what we call multi-planet systems. And there's actually a really great video I should probably show, because this shows one of those that was found that has 6 planets orbiting the same star. There's actually a nice audio that goes with it, but it sounds like it's not playing. It's like this. This is known as the Kepler-11 system, and the discovery. Oh yeah, there's the audio. Someone made a video of this where every time a planet passes in front of the star, they have a different tone, so you can hear each planet as it goes around. So this is 6 planets orbiting the same star. These are 2 different views. So this is the view as we would see it from our perspective, and then this is the view as if you're looking down in that stellar system. And you can see, of course, the closer planets orbit more quickly, and the more distant planets take longer to go around. But the interesting thing is that all these planets are interacting. They're gravitationally bound to the star, and they're orbiting the star. But every time 2 planets pass one another, they tug on one another. And so if this is the star here, and these are 2 planets, then the inner planet's moving faster, and when it catches up with an outer planet and passes it, gravity becomes stronger as 2 objects are closer to one another. And so when they pass each other in their orbits, they'll give each other a kick, gravitational kick, caused by gravitational attraction. And this is actually this is something that Newton's described. So the force that a planet exerts, F, is equal to the mass of that planet times its acceleration. So in other words, when another planet passes by, it's going to exert a gravitational force on that planet. The way the inner planet, let's say, responds to the outer planet, which is the acceleration, which is how fast it's going to change its speed, depends on the mass of that planet. And now let me put some numbers on here. So the force, let's say on planet 1, due to planet 2, this is the only equations I'm going to give in this talk, so don't worry, is equal to the mass of that inner planet times its acceleration. This is Newton's second law of mechanics. Newton also discovered the law of gravity, which says that the force between any two bodies is equal to Newton's constant, g, the universal constant, times the product of the masses of those two bodies divided by their separation squared, where this is the separation d, or distance between them. Now, if you combine these two equations, what this says is that the acceleration of the inner body is equal to g m2 over d squared. This is a really profound equation. So Newton showed that your motion, or the acceleration of your motion through space, which is determined by gravity, is determined not at all by you. There's no one that appears on this right-hand side. There is the distance that you are from anything else in the universe. But your motion is only determined by the masses of everything else in the universe. So if you ever get a kind of a weird feeling of helplessness that you can't describe, this equation describes why. Because you have no control over where you're moving or where you're how your motion is changing through the universe. It's only everything else that has control over that. Yeah, on the freeway, for sure, yeah. There are other forces that operate in the freeway, unfortunately. Okay, but what this means then is that by looking at the transits of planet 2, for example, that's being accelerated by planet 1, and so we can measure the mass of planet 1 by looking at planet 2, and vice versa. And so each planet tells us about the other planets in the system. Okay, so...
But the acceleration of 2 is also totally dependent on 1.
Exactly, yeah. Yeah, I could write down the same equation, flipping the numbers. Yeah, so... Okay, so then the question is, how do we use this to measure masses of planets? And I'll go back to this planet system that I showed you earlier. So this, you can see these dips every time a planet goes in front of its star. Turns out this planet is about the size of Neptune. And one way to represent this data is to take each of these dips and just align them in time. And now instead of plotting on this scale, I'm going to change it to a color scale. And this is something we call a river plot. So this is the river plot for this planet. So the same data, just with a different representation. Where blue is where it's dimmer, the star is being blocked by the planet. This is a shadow cast by the planet. The color scheme we chose is just because it makes it look like a river with a nice grassy bank. And so what this shows, this is time in hours, and it's been aligned every orbit, every 16.7 days that this planet orbits in front of the star. We plot another row of the brightness of the star at that time, so just over 20 hours out of that 16.7 days. So each of these rows here, we're seeing another planet. We're not seeing it directly, we're seeing its shadow. And this, you can clearly see the planet. The blue and green are very distinct. Now, what is this river shape here? Well, that's the acceleration, which means there has to be another planet there.
Huh.
The gray is where data are missing.
Huh.
And the Kepler spacecraft had to send data back to Earth, and so that caused gaps in the data taking, which is kind of unfortunate. So there must be another planet orbiting the star because of its change. What's happening is its orbital period is changing. Sometimes it's arriving later in its orbit, sometimes earlier. The Earth does this too. A year is not a year. A year is actually changing by a few minutes because of the tug of the other planets in our solar system. And so the really large changes here make you wonder what's causing this. Initially, there was only one planet found around this star. And if you look at that data I showed you, you don't see evidence of another planet. Now, you can try folding this data. You can remove this planet's signal and fold the data on different orbital periods. And the Kepler team that runs the Kepler spacecraft has a software program that does this. And they failed to find another planet initially. We developed a new technique for looking for planets that might have irregular orbits. And when we did, out popped the left-hand plot. And it doesn't look like much. This looks more like a marsh than a river. And that's partially because it's a really small planet, which is really exciting, because it's only about 40% bigger than our Earth. And because it's such a small planet, though, that quantum noise, these blue and green colors you're seeing here, it's a smaller depth. The scale is slightly shallower than this depth on the right. But the blue and green here you're seeing is actually just the quantum noise from counting photons coming from that star. But when you allow the planet's orbit to change with time, you actually get a really good fit to this data, and you can see it's slightly bluer within that center. And the really cool thing is that it mirrors this other planet. This didn't come out of our detection algorithm. We didn't force it to be the opposite of this planet. We actually just searched for the planet, basically allowing any time to be possible for every transit within some window, and that allowed us to detect this new planet. So this is now is known as Kepler-36 b and c for the inner and outer planet. This planet orbits every 13.8 days, I believe. And you can see some remarkable things, like you can see these sudden jumps in this curve, and that's actually when the planets have a close approach. And gravity is strongest when you're closest, and so you suddenly change the periods of the planets, and you actually change the shape of their orbits slightly.
What star is this? And how far away is it?
It's about roughly 2,000 light years away, I think is the number, and very far. And that's part of the way Kepler was designed. How much of the sky it can look at limits it to looking for more distant stars. If we're looking over the whole sky, then it could cherry pick the brightest stars in the sky, which are the nearest stars. Am I wrapping up in about 5 minutes? Okay, so this data, it might remind you of the most famous body of water in Southern California. Does anyone recognize this body of water?
We don't have water.
That's right.
It's the Rivers of America ride at Disneyland. I was just there with my kids last week. Okay, so with that data, with that river plot, we can actually model that. We can model the gravity of the two planets as they interact, as they go around the star. We can model the depth of the transit, which gives us the size of the planet. And what we get is a very precise measurement of the radius of these planets versus their mass. And this is in units of the Earth. So the Earth is at 1 because its radius in units of the Earth is 1. In units of mass is 1. So the planet that was missed initially that we found is this Kepler-36b planet. It's about 4.5 times the mass of the Earth and about 1.4, 1.5 times the radius of the Earth. And what that means is that if you took the Earth and you increased the Earth's mass, keeping its composition the same with an partially iron core and rocky mantle, this dotted curve predicts what size this planet would have at this mass. And it goes right through the center of the probability distribution that we derived from this data. So this planet seems very, very similar to Earth. The other planet, the planet that was found first, because it's bigger, has a larger radius, so it makes a bigger shadow. It's about 3.7 times the radius of the Earth. And that puts it about just a little bit smaller than Neptune or Uranus, which are out at larger masses. And so this planet's about half the mass of Uranus or Neptune, but about the same size. And that's actually predicted by models, which are shown here. The dashed dot curve has a model in which there's a rocky core, so something like this portion of the dotted curve, surrounded by a hydrogen and helium envelope, which is those are the most abundant gases in the universe. And that can explain the size of this planet nicely, with just 7.5% of its mass in hydrogen and helium. Hydrogen and helium are very low density, and so they fill up most of the volume of this planet, if this is the correct model. There could also be layers of water or other elements, and that is ambiguous. But if you want to make something similar to Uranus or Neptune, then this is what it would look like as far as its composition. So this is really weird because these two planets orbit around the star in 13.8 and 16.7 days, which is a ratio of about 6 to 7. These are the closest two planets that have ever been found to one another. Extremely close, both fractionally in their orbital period and in absolute proximity. Although there may be some other planets that have been found since then that have slightly superseded that. So they're very close to one another, and yet they have very different densities. This is denser than the Earth, because as planets become more massive, the gravity starts to compress the rock, and so this is denser than the Earth. But that's exactly what you predict if it were Earth-like composition. This one is like the density of water. It's about the same density of water. So the ratio of their densities is a factor of 8, which is kind of surprising. There is an explanation for that, but that was a big surprise when we discovered this. Now, because these planets are so close, if you stood on this planet and looked out at that one, this one's about the size of Neptune. So I'm living in Seattle now. This is the moon, full moon above Seattle. If we were to take and replace the moon with Neptune and pull Neptune as close to Earth as these two planets are as they pass one another, then this is the view that we would have from Seattle. Now, of course, these planets orbit very close to the star, so they're extremely hot surfaces, so Seattle would be molten. But if you ignore that fact, this is what it would look like. So this is a really remarkable planetary system. It gives us the most precise measurement of a so-called super-Earth mass planet and shows that it's similar to our Earth. But it also has this really large mini Neptune, about half the mass of Neptune, that orbits extremely close. Okay, so that's about all I had. The future looks really bright for this field. We're going to get more masses of planets and radii. I'm already working on that. There's lots of ground-based follow-up we can do. Some of it from a Santa Barbara perspective with the Las Cumbres Observatory, which is located over here in Goleta, but also the Keck telescope, which the University of California has a part of, and it's building a 30-meter telescope, which will be the successor to Keck. There's some NASA planet missions, which are really exciting. Kepler has been repurposed as what's called K2, looking at other parts of the sky. There's a new mission being built called the Transiting Exoplanet Sky Survey, which will survey the entire sky, albeit with less capability than Kepler, but it'll be able to look at all the bright stars around the sky. And we're about to launch a successor of Hubble called the James Webb Space Telescope in a couple of years. And with that telescope, we can possibly do very precise characterization of some of these planetary systems. Eventually, we'd like to find more Earth-like planets, and we're on our way, actually, with Kepler, which would be a whole other talk. But the hope is to eventually see directly whether there are planets like the Earth orbiting other stars with a future space-based mission. So, thanks.
More questions, please.
Yep.
I know it would be impossible to detect with any of the methods you've been talking about here, but is there a possibility of free planets not associated with any solar systems wandering out there?
We just had a discussion about this morning at 10 a.m. So,
You didn't invite me.
Yeah, I know. You would have gotten your answer there. There are some really exciting recent discoveries with the microlensing technique, which I didn't have time to go into, but the basic idea is that you look at a bunch of really distant stars, and if a star or a planet happens to pass in front of that distant star, it can magnify that distant star. We've actually detected a microlensing event in the Kepler data, which is exciting. But this technique has been used to find stars in our
Beyond
galaxy and find planets orbiting those stars. But it's also found these little short period brightenings that last a short enough amount of time that they probably aren't stars. They might be free-floating planets. But the interpretation of the data is right now kind of fuzzy. We don't really have enough detections. There's really two kind of certain detections that have been made. There's a lot of ones that don't look quite so good, and so we don't yet have the statistics of two events to be able to conclude how frequent free-floating planets are. But it's quite possible, it's probable, in fact, that our solar system created other planets or planetesimals that got ejected at some point. So there might be quite a population of those.
Michael?
What's the story on exomoons?
Exomoons is something that I've looked for in the Kepler data and have yet to find anything. There's a postdoctoral fellow at Harvard that's hard at work trying to look for moons via the transit technique. You'd see a little shoulder on the side of that transit shape due to the moon. But the precision of the data of Kepler, due to the fact that a lot of the stars are far enough away that they're dimmer than we'd like, means that it may be hard to detect exomoons in the Kepler data if they're similar to moons in our solar system. I've been thinking a lot about this problem, though, but I'm hoping that we'll have a detection maybe in the next decade or so, if they're out there. Yeah.
So because our Earth is where it is on that graph, we're kind of unusual in this.
Well, so like I said, this is highly sculpted by what we can detect, and these are the easier planets to detect because they're bigger and they're closer to their stars.
So maybe a detection thing?
So yeah, so the planet, one of the planets I found is about would lie right about let's see, we don't know its mass quite yet, but somewhere around here, which is getting pretty close to Earth. There have been other planets that are found that may be even closer to Earth. They're actually closer to their star because they orbit really dim stars. But the star is so dim that even though the planet's close, it could have a temperature similar to Earth. So this is probably one of these points in this region, which I haven't highlighted. We're hard at work trying to detect these planets. The Kepler data weren't quite up to what the specs were initially hoped to be. It was initially hoped that Kepler could observe for longer at the same field of the sky and then build up better statistical sensitivity to smaller planets. But because of a failure of one of its reaction wheels, that had to be scrapped. So it may require this transiting exoplanet survey, sky survey that surveys the entire sky, but that one, because of its design, it turns out may not be exactly sensitive to Earth either, which is unfortunate. So we're trying to push down here, but it's technically very difficult.
How many years away do you think?
Optimistically, 5 to 10 years. I think really the way to go now is to do direct imaging with a new telescope in space, which I could go into more. I have some slides on that. Yeah.
So I have two kind of related questions to this. Do you have any comment on what the probability of the plane of the planets lying in front of the sun is as a function of their astronomical unit separation?
Yeah.
And do you have a comment on kind of how many times the planet has to go in front of the sun before you can detect it and call it a planet, and how that depends on how far away it is?
Okay, yeah. So the two good questions. So the farther a planet is in distance from its star, the probability of it aligning to cause a transit goes as 1 over that distance. It's equal to the radius of the star divided by the distance of the planet if it's a circular orbit. And so that's really why there's no red points out here, because the geometric probability is small, and these planets take a longer time to orbit their star. Kepler was only up for 4 years. If a planet's big enough, then you can detect it with 1 or 2 transits. If you only have 1 transit, you don't know its orbital period. If you have 2 transits, you can judge its orbital period. If the planet's small, then you have to worry about stellar variability because stars do vary. But so usually the criterion that's been applied for Kepler is to have 3 transits. And actually one of the planets I found had 3 transits initially, and when I saw that 3rd transit, it was really clear it was a planet because it was exactly spaced by 267.4 days between 3 transits. That made me really sure it was a planet and not some stellar variability. So 3 is the criterion. But to get 3 transits means 3 orbital periods. And so out here, Kepler didn't fly long enough to detect those planets. Yeah, even if the geometric probability was such that you could see them.
So I guess, for this big red group, do you know what the probability is, of the planet lying in front?
Yeah, so these are typically in the range of 10 to 100 or so probability per planet. And so then you can correct for that and calculate how many stars have planets. Every star must have planets, basically. The uncertainties on that right now are fairly large. Every star must have planets is likely the case because we're only detecting these close ones, and there's bound to be ones further out that we can't detect. You have to do a bit of extrapolation to get out there, but if you believe there's that extrapolation, then probably every star is a planetary system, which is pretty amazing.
Yeah, I was just wondering, with that big planet, almost the size of Neptune, up close to the planet the size of Earth, that close together, wouldn't their orbits be likely unstable? I mean, you're not going to.
That is a really great question. So I unfortunately dropped that slide from here, but you can actually show that planet system is chaotic, and that on a time scale of like 10 years, you can't predict precisely where the planets will be. And it does appear to be stable, though, in a sense, with something called bounded chaos, where the planets' orbits are hard to predict, but they never get too close to have something disastrous happen, which may be why we see them now, because the star is pretty old. If planets have been around since the birth of the star, then they would have to be long-term stable.
Do you think that could explain? Oh, I'm sorry. Do you think that could explain why you're seeing planets where you wouldn't expect it to, because it's called three-body problem or something? Where they
Yes, yeah, and that, in fact, that is the main explanation. So the question is that why we see some of these particularly close-in planets? This clump of planets up here that are size of Jupiter but orbit around their star, and if, in some cases just a handful of days, these are thought to. Now I think the favorite explanation is that these are caused by three-body interactions, whereby another planet, let's say you started off with a Jupiter out here and maybe another massive planet or another distant star, the gravitational interaction of that can cause this planet to become more like a comet, and as it passes closer to the star, then eventually circularize in its orbit and end up in this location. These are called hot Jupiters, and because they're so close to the star, they're extremely hot. And there's some evidence that these may have been formed by three-body interactions.
Yeah.
Yeah, you say by Kepler, you take a look at the transits to locate your planets, and some fraction of planetary systems are amenable to that because of the orientation of the orbits.
Yep.
By the blue method, you can detect them by different methods.
Yep.
If you look at all the planets that, say, Kepler is looking at, and maybe you find 10% have planets by your transit method, and you can say, well,
you can correct for that, Jim.
That might mean all of them have planets, we can only see 10% of them. What I'm getting at is, by all methods, of all the stars you can look at, what fraction of them do you think have planetary systems?
I think it's 100%. And again, that involves some extrapolation to smaller masses and to larger distances, but the data seem to be pointing to at least 50%. But my guess is it's more like 100%, and that 50% I think is probably conservative. So it's pretty, which in hindsight maybe not so surprising. If the sun forms planets, then maybe every star should, but we didn't know that until we started finding
it. Might really be billions and billions.
Yeah, exactly.
Yeah, I was just wondering, to what extent would like Oort clouds or asteroid systems diminish your chance of seeing or being able to detect stuff?
That could be a big problem in detecting other planetary systems. This shows a diagram of what the solar system might look like with a large space-based telescope. So this is kind of beyond the James Webb Space Telescope. We've called it the Large Ultraviolet Optical Infrared Explorer, or LUVOIR for short. This is just a pie-in-the-sky concept, actually, of a sort of 15-meter telescope. You can see segments. This cannot be built yet, so this would be maybe 30 years away. But potentially you could outfit this with a...
billion or 50 billion?
Yeah. Well, kind of, yeah, so, okay, cost is a whole other issue. I have a whole slide on cost, actually. But the cost has been going down. So if you look at the cost from Hubble to Spitzer to James Webb, if you look at the cost per unit area of the telescope mirror, which is what astronomers like, that's been going down. And so if
no units on this axis.
I know, exactly. So that, if it continues to decline, then maybe we can build a larger space telescope. So,
do you have any comment on using an interferometer in order to get enough resolution to see?
That's another approach. So this approach, this is the interferometer approach, actually, I put it by mistake. So the one is that LUVOIR, which has a coronagraph, which blocks the light from the star, and then you can potentially see the planets. But you see all this cloud of dust also orbiting the sun, and that can actually, in unfavorable instances, that could block your ability to see a planet. But if you build a big enough telescope, this spot becomes tighter and tighter, and it's easier to pick up the planet relative to all the dust within the system. And then, so one way to do this is with a large telescope with a coronagraph that blocks the star. Another way to do this is to fly a fleet of telescopes and interfere their light and suppress the star that way, and then detect the planets.
Last question.
Is there a problem with these gas giants being so close to the hot sun? Are they short-lived or even not even possible?
That's a really good question. So They're massive enough that they should be long-lived, but there's this interesting effect that some of them appear to be extremely large, like twice the size of Jupiter, which would require a lot of heat to be input into that planet to puff it up, because it turns out that most planets that are cold, the biggest size they can get is Jupiter as far as radius. This diagram shows mass, and so it's a different, even though these planets are more massive, they should still, if they're cold, be about the same size as Jupiter. But a lot of these hot Jupiters are much bigger than Jupiter is, which means they have to be very hot inside. And what that heat does and how it got there is still an unsolved problem. But they should still be long-lived. It may be that some planets down here got evaporated by their star, and that's why we see a Earth planet. And as they're evaporated down to their core, then they'd be a smaller mass and also smaller in size. But a Jupiter or giant-sized planet could still survive that close to a star potentially.
All right, let's thank
Yeah.
Eric.
Yeah.